Okay, so it's 7:05, and I will start. And this, currently I see only 11 people. See, so when I will start, and then people will start joining. So that's little irritating. Anyway, I have to start. And those who have joined earlier, thank you very much. And let's start. I will share my slides, which are pretty easy. Yeah, I know. Okay, anyone just please respond in message chat box that my screen is visible or not. You can see my screen, right? Yes, thank you. Thank you, Jai Kumar. Okay, thank you also. So let's get back to our business. Okay, so I have my periodic table here anyway. So welcome to day 2 in PTL Mechanism in Organic Chemistry. This is a tutorial session, and I will refer to these books: Peter Sykes, NRT Morrison, and Aaron Boyd, and also I will show some figure, and I will use the book by Clayden and others. See, so that's the problem. And here I go. Okay, so again, so I will be little bit slow. Okay, otherwise people will come on again. Hmm. Now, in the first slide, itself, there is people are joining. Admit. Please, whoever are joining after 7:5, try to attend at 7 below before 7:5. It would be helpful. No problem. And then go ahead. So my first slide itself shows that 1 2 versus 1 4 addition, and this example is related to with 2 lecture, which has what are the things like, first of all, reaction coordinate diagram. Reaction. Okay, come on. Admit. So which has a discussion about reaction energy profile diagram, and then Cartin-Hammett principle, Hammond postulate, uh, thermodynamic, and then kinetic control product, thermodynamic control product, kinetic control product. So overall, so in this slide I will talk about reaction profile, that is energy reaction coordinate, which is the typical profile looks like. In the y-axis, what you see is potential energy, and in the x-axis you will see uh, reaction coordinate, basically some geometrical parameter. And in this slide I will also talk about kinetic control and thermodynamic control. And this slide, I mean, this question is also talked by ma'am also in our class. Anyway, I will go through it. So we have been given within this simple equation, simple reactant. Okay, so what we have an diene, at the left side we can see, and then we are adding hydrogen bromide HBr, which is the source of H plus. Now H plus, it will like electron, electrophilic, and this double bond, which is electron rich, it will attack, I mean, it will attack an H plus, and it will form an carbocation. So what I told, I will show. So basically I will try to show the mechanism first. Okay, so now let's go ahead. So this is a typical reaction. So when we have 40 degrees Celsius, remember we have 40 degrees Celsius, what we get is a mixture of product, in which 20% is this product. At the left side my cursor is there, and the right side it is 80%. You may have seen this reaction, but anyway, this is a very general reaction, kinetic and thermodynamic control, so I will discuss. And this is a condition, I mean, in 40 degrees Celsius you have a little high temperature. I will show you something in the left also. So what is there? Minus 80 degrees Celsius here, and you see the product two are, of course, they are same, like this, which is shown in the left, right side also, and this also is shown in the right side. But see, the difference is the their distribution, meaning that here in this bromine, whatever obtained in the 40 degrees Celsius, 20% and 80% is just got reversed in the minus 80 degrees Celsius. Or you can start with minus 80 degrees Celsius. Whatever your product got, major and minor, it gets reversed in the 40 degrees Celsius. Now another observation is that let's say you do the reaction minus 80 degrees Celsius, and you increase the temperature, and at 40 degrees Celsius you got this one. So basically just by increasing the temperature you got to the product which are obtained for 40 degrees Celsius. This is the problem or observation or fact, right? Now I have a couple of questions which we will try to address. What are those? Let's see. Can we draw the mechanism? Yes, we can. How do we account for the temperature dependent selectivity? For example, when we have different temperature, we are getting product ratios are different, right? So that is a second question. And we have also another question, gives for the reaction profile diagram. Can we guess it? And so this temperature dependent observation we will try to show in a reaction profile diagram. Okay. And so let's do it. And I have book with myself, and sometime I will read from book also. So please stay with me. I hope this question is pretty clear and it is easy to do. Now I will come here. Okay. So I need a whiteboard. Let's go to starting whiteboard. Just a second. Share with people. Just a second, okay. So what we have is an alkene. Sorry, dye. And then we have HBr. So someone want to get joined. Meet Rishi. Welcome Rishi. Please try to join early. Okay. Now what we have is this will attack here and this will go there. So what do we get actually? It's very easy. Now there is a question, where will the hydrogen will add? Let's say if I put number 1, 2, 3, 4. Since you know which carbocation is stable, so I will directly jump into that. So I will add hydrogen here. So CH2 will become CH3 now, and there is a positive charge here. Now what will happen? We have Br minus, right? So it will go here and it will give us the product. Am I drawing right? No. And okay, so here we'll get the bromine, which is shown as for example, if I go to here for minus 80 degrees Celsius, this as the major product. If I check in my book also, yes, it is the major product at minus 80 degrees Celsius. So imagine we are doing all these things in let me change the color, it will be easy. Minus 80 degrees Celsius. So it has the overall, it has a low energy, right? Temperature is low, energy is related to temperature. And what is the other product? The other product is obtained from if the hydrogen adds to the second carbon atom, according to my numbering here. So if I do it, I will have, so it will, hydrogen will add at the second carbon, so there is a positive charge here. And then what will happen? I have again Br minus, which is very easy, and I'm showing it arrow here. And so there you go, Br, and the number is 1, 2, 3, and then 4. Nice and easy. So if someone asks you why is this as formed as 80%, this has formed 80%, and this has formed as 20%, right? So the typical answer is that since this carbocation, which is 2 degree, is more stable compared to this 1 degree carbocation. It's simple. Wait.
So,
Yes, 1 second here. View all, admit all. Perfect. Yes, who is this? And please go ahead.
so double bond will conjugate and then we got the product.
Yes, of course, I will come to that point. So you have gone ahead. But now, whether you agree or this not with this mechanism, whatever I have done in kinetic, this minus 80 degrees Celsius. Hello.
Yes, sir.
Yes. So that's how you observe. I mean, explain this observation at the left side, right?
So in this very first slide,
Hmm.
you have bring kinetically controlled product to thermodynamically controlled product in just by changing minus 80 to 40.
Hmm. Yes.
It actually happens in reactions.
Yes, that's the case. That's the situation actually. So, what do you think? It's awesome, right? I mean, it's unusual how it will come back to this point, right?
Yes, sir.
So the it actually it's written in the book, and I will discuss also. So you just stay with this, and you will get to know. So how it will get back to the these things. So that will come from the energy profile diagram reaction coordinate. So if you see that, it will come. So this part is pretty clear now. And now at 40 degrees Celsius, so if I just change the color and let's say take this one now plus 40 degrees Celsius. Now let me ask you one question. So now I will talk about the stability of the product. So this time I was talking about only the stability of the carbocation, right? So this carbocation was more stable and this was the less stable. Now in terms of stability of the product, now what are our product? Our product is this one and this one, mixture of product. Hmm. Now what do you think? These two products are terminal alkene, right? The alkenes are the terminal position. So something is wrong. Do you know what is? Yeah, something is wrong. What I've shown is there. So someone told me that conjugation. Please tell me your name. Hello, are you there?
Yes, sir. I told.
Okay, okay. So actually, see what I've shown is the not the product here. You got it? So that's what you
Yes,
were
sir.
saying. There is a conjugation and then product is different. Actually, this is not the product. Sorry for that. I will change it just a second. So actually this carbocation is not formed at all. My point is this carbocation is formed not at all here. So this form second actually it is formed. So I will go with it. See, so if there is a conjugation here, my alkenes are the terminal position, but both the products are not at the terminal position. See, double bond has shifted. So that's what I've missed. So if it goes here, so if it goes here, so what will happen? So this will come, double bond will come here, and then methyl, and this plus as here. But these are two different, right? For example, if I name it one in black color, and if I put it two here, so these two are not same. So though both are this also has 1 degree, this also has 1 degree, but it has a conjugation. So you are right. So here there is a conjugation. So overall this 2 degree will form. So but this is also has a chance, maybe minus one, sorry, maybe 1% or something less amount. So this will very minute amount may be possible. But overall it will form only this carbocation. Okay. And here this will undergo let's say, well, I don't have space. Uh, wait just a second. So this there is a no question of these things. So the primary carbocation is not forming. Okay, so no problem with that. I will directly move into here. So here if bromine attacks, so I will show the arrow here again. So this one, it will give us the product which were mentioned in the slide actually. So double bond and then CH3 and there is a CH2 and then Br. These has formed as a 20%. So this is the product. So my point is that we get this carbocation initially. The proton will obviously attach at this first carbon atom here. Then it's got a secondary carbocation. Now since it is conjugated with this alkene, so it can move here. And the plus charge will come here, which then attacked by bromide Br minus and give us the 20% product. Now it makes clear. Okay. Now let me ask you a question. So this is clear for minus 80 degrees Celsius. Now which product is more stable? So which product is more stable is easy to answer. So this is the terminal. This is the terminal alkene. This is the alkene is the terminal position. Whereas in the first case, the alkene is the disubstituted and in the middle. So we can expect that if I put name alkene A here and alkene B, the stability order will be A is higher stability than B, or in terms of energy, A has lower energy than B. This point is clear to you, right? I hope it is clear. Now I need to draw again something, so clear the frame. Hmm. So what we have? We have a general carbocation, a common carbocation. This carbocation, which I can draw resonating structure, like double one will come here and then there is a plus. These two are the thing. Hmm? And say, let's say I will represent, so in the y-axis, let's say we represent potential energy E. Hmm? So I will try to connect from the reaction mechanism and then kinetically controlled and thermodynamically controlled product to the reaction energy diagram profile. So energy increases in that way. So let's say if I put a uh, horizontal line here representing the carbocation here. So this carbocation, it has energy, and in terms of product, so we know that for example, if I do minus 80 degrees Celsius, in which way? So let's say minus 80 degrees Celsius in this side, which we have shown. So the product which is more stable, so there will be two things. So there is a one product, let's say here, and we say the terminal alkene is less stable. So terminal alkene is less stable, but this was formed as the major product, and so it will have associated one transition state. So this corresponds to a transition state. So my point is that and the activation energy I will represent like this. So the reaction is, it has a, I would say, I'm not I should have compared, but anyway I'm saying that it is a very low activation energy is low, minus 80 degrees Celsius, and it can easily go and forms the product, which is the, this was the major product. So this just a second, okay, let me check here. So this where carbocation was more stable, so this will give us the corresponding major product. So let me write terminal alkene. So this was the major product, but in terms of alkene stability, this is less stable because the alkene is in terminal position. Now whereas I will go to now this 40 degrees Celsius situation, what will happen here? So already I have shown you the question, and it is shown that the more stable alkene is formed as product. So as soon as I say that the more stable alkene is formed, meaning that it will come from this side, because the alkene will be formed here much more stable. So much more stable meaning that it will have lower energy corresponding to this point. So corresponding to this point, if I draw a line here, so I will draw the product here. I'm talking in terms of only major, okay. So here the product will be this one. So it's more stable. So more stable, let's say I forgot the name earlier, but let's say I put A here. This is B. Now how do we what will be the activation energy? So from the temperature itself, it's we can say that it requires high temperature to come to this point, to the more stable alkene. So high temperature means you need high energy to put, which in turn, so I'm giving high temperature, high energy is given, which in turn will mean that you need high activation energy to overcome. So I will draw the corresponding okay, let's say it jumped, so it will be like this, and this will be our transition state here. Let me give a name ts1, and this gives as a ts2. So it has a, when it has a high energy in 40 degrees Celsius, so it can overcome this activation energy, which is little higher. So the activation energy, and this is corresponding to 1,4 addition. 1,4 addition, and this correspond to 1,2 addition, right? And wait, just a second. So what happened here? Let me read some sentence. So let us examine the matter of 1,2 and 1,4 addition more closely by drawing a potential energy curve. So this is the potential energy curve for the reaction involved in this figure. The carbocation initially formed. So this carbocation, which is initially formed, reacts to yield the 1,2 product. So this is the 1,2 product. So hydrogen adds here, hydrogen is adding here, and bromine is adding here. Faster than the 1,4 product, which is this one. Faster than the 1,4 product. 1, 2, 3, and this as 4. So this is slow, so higher activation energy. Consequently, the energy of activation leading to 1,2 product. Consequently, this activation energy leading to 1,2 product must be less. So this must be less than that leading to 1,4 product. This one. So that's why these figures look like this. We represent this by the lower hill leading from the carbocation to the 1,2 product. So that's why lower hill compared to the higher hill here. Now please listen me carefully. More collisions have enough energy to climb the low hill. So more at the lower temperature, any collision will have certain extent energy, and it will leads to which is sufficient to climb this hill, but not sufficient to climb the hill. Minus 80 degrees Celsius, the collision energy, which is enough to go to this, cover this path. It can go and cover and jump this path, but that energy is not sufficient to cover this path. Okay, so it is not sufficient. Thus 1,4 product however is more stable. So this is more stable at minus in any temperature. It is more stable, but it cannot form this. We must place its value at a lower level. So lower level than the 1,2 product. Okay, and so now I will come to this, how this conversion happen. So if I now this point is clear, right? Now the question is, if we increase the temperature from minus 80 to 40 degrees Celsius, it will revert back to this point. Now how this will happen? So this happens because, so it will start from here. My screen is become getting dust, not good. Let me change the color. So what happened? There is a statement written. As we know, allylic halide. So this is an allylic halide. Remember. So this is an allylic halide. Product B is an allylic halide. Readily undergo heterolysis. So you understand what is heterolysis? So it will again break, and it will form the carbocation back again. So this, it can at 40 degrees Celsius, it has the energy because you have a high temperature. So it has the enough energy to undergo hydrolysis. So it will come back to the carbocation again and the Br minus form. So as we increase the temperature, this allylic halide will undergo hydrolysis to form the carbocation and then Br minus. Now, since I am in 40 degrees Celsius, which is high energy, so it will, what will happen? It will attack at this carbocation, basically the same carbocation, but the temperature is the factor. Now it has enough activation energy here. This much is there, so it can lead to the correspondingly more stable product. So that's the situation which is described here. So when you give 40 degrees Celsius, the allylic bromide at the left side can undergo hydrolysis and form the carbocation back. And since now it has a high energy available, so it can go to the more stable, this 1,4 addition product. Overall, this is the main point here. And just a second. So let me read this. At temperature high enough for equilibrium to be reached, that is high enough for significantly fast ionization. So there will be fast ionization. the more stable 1,4 product predominant. So that's why we get the products. That's why we get the conversion. And so this is the situation here. So overall reaction profile diagram, how it changes from -80 to 40 degree. What is the thermodynamically stable product? What is the kinetically product? So this we call as the kinetically controlled product, and this we call the thermodynamically controlled products. And that is the situation here. And let me go back to this. So anyone have any question? For today we have 14 people only.
Sir, in
Yes.
sir, here could also you show that any transition state between the carbocations, which one carbocation converted to this, another this maybe transition stage conversion. Is it low in
So you were talking
activation?
about the why I am showing the only single carbocation, right?
Actually, one
Hmm.
carbocation will convert into another, then only will other product will form. I have
So you are
seen.
talking about this carbocation conversion.
So in the
Uh,
reaction
uh,
graph,
uh.
coordinate graph, will want to show that it's a transition state of one carbocation into another.
So let me clear you one thing. So see, I showed and see these are resonance structure, right? So that's why I show this arrow. So these are resonance structure. So don't think that these are two different structure. So what happened actually, I will show you. Let me clear the frame. So you have these are canonical structure. So you have plus here, and the corresponding canonical structure is, so there is no conversion. It's the single carbocation. Sorry. So I can draw the double bond here, and this is the plus. And what is the actual? So overall, that's very poor. So it is like this. The plus charge is distributed overall all three carbon atoms. Remember, these two are not, they are distinct separate. These are resonance, so which doesn't have any. These are not actual. Remember, these are theoretical concept. So these two structure, these are theoretical. They don't exist like this. Okay, this is for ourselves. Actually, it's this single carbocation. Remember this point. So there is no conversion between this and this, but there is. So yeah, what initially I showed, and then you asked the carbocation will undergo resonance. Actually that was true here. The proton can attach at this point 1 and then 2, but we showed that this carbocation is stable and it will not form. So rather this carbocation will form, and so there was chance of this carbocation may equilibrate and other things, but there is no equilibrium between these two carbocation. So equilibrium is there in when, so let's say allylic bromide was there, right? So this allylic bromide, it can undergo equilibrium to the so carbocation back and then bromine minus. So there is the equilibrium here. So at -80 degrees Celsius, it generally what happens, it directly attack here, because it doesn't have enough energy to undergo the one for addition product. But when you give 40 degrees Celsius, it will undergo break here, and this time it has higher energy to overcome. It has enough energy to overcome. Just a second, huh? Admit. Did I answer your question?
Yes, sir.
Okay, thank you. And any other thing? Please let me know. I will try my best to answer. If you find anything wrong, then just let me know. I will try to correct those. Thank you. And let's go to the slides and what are there in the next question. So overall we try to draw the mechanism what we tried, and then how do we account for the temperature dependence, how it come from to this, and the reaction profile diagram. Now I see, if I show the reaction profile, I started directly from the carbocation. So imagine a single person is going to one path, single path, and then come to a point, then it bifurcates, so then there comes two paths. I can go to this way or that way. So initially, let me discuss some more. And clear the frame. So first step is was like a normal. Huh? So it forms a carbocation. Carbocation it forms. Then there is a chance. So it can go high energy pathway or low energy pathway, which become in temperature dependence. So initially the alkene it forms a single carbocation. Actually, not even not that also single carbocation. And that's what I shown in the first time. I mean, which I was doing. Actually, there is also two possibilities are there. The plus can be formed here, and then plus can form also here. So these two are actually possible. And so this is the situation. And let me go to the other thing right now. So there is one more question here. Yeah. Again, our very known reaction, electrophilic aromatic substitution reaction, and this is a nitration reaction. And we will try to draw the reaction profile again. Reaction profile. So I have a couple of questions here. Let's see. So what is the mechanism of this reaction, which we will show, and what is the rate determining step? Furthermore, what is the evidence of these things? So this, please remember this 2 point: mechanism of the reaction, what is the rate determining step, and the evidence. So this evidence will come from a kinetic isotope effect. So I'm not sure all of you have gone through the week 5 lecture or not. I thought to introduce here, but I will go ahead. So all of you know kinetic isotope effect. Have you gone through the lecture week 5? I'm not sure. Anyway, let's go. Just a second. Before I go there, 517. Okay, I am here. No problem. And then let's start with this simple question. So I hope you are aware of this reaction. It's very easy. And so this is the benzene, our favorite molecule. Hydrogen. So all our hydrogens are there. Okay. And then we have the corresponding electrophile nitration. In nitration, the electrophile is NO2 plus. Now, if I draw the mechanism, so if you remember from the MAM slide, so how do you propose the mechanism? So initially you guess something. Okay, this is my hypothesis. You do the experiment. If it is matches, okay, that is the mechanism. If it doesn't match, you propose a new hypothesis, and again you check by experiment. Okay, so we'll do some similar situation like that. Now this, what will happen, this pi electron will attack here, and what we get, an intermediate like this one, and there is a carbocation formation here. So this is the first step. Okay, now this has some canonical structures which I am not going to draw now. So let's say step 1. So this is our initial hypothesis, first hypothesis. Okay, so H1, hypothesis 1. So we are assuming that it will go via through this mechanism. Okay, and then in the second step there is a hydrogen elimination. So it's like this. I shouldn't draw like that for the time being, to make confusion. So this is the product plus H plus. So all of you are aware of this mechanism? I hope so. So this is a typical let's say our first hypothesis, that we are getting the nitrated product. Let's say we name it A. We get this through this two step. So step 2. right? Why not? Let's say some of us, let's say propose a new mechanism. Let's say hypothesis two. We'll show the reaction coordinate. Okay. Let's say someone propose a new mechanism hypothesis. What he suggested is that it's a single step mechanism. Let's say someone suggested rather than let's say being a two step, we can think it of as a single step reaction. How single step reaction? Maybe the hydrogen carbon hydrogen bond breaking at the simultaneously. So I am showing in a dotted line. Okay. And the bond formation at the NO2 is also simultaneously. So this bond is getting break and this bond is forming. And if I show the arrow, so remember there is a plus. Okay. And so what happened at the very first step, which is like very kind similar to SN2 reaction, and then we get NO2. So this is our hypothesis 2. So as Nam already told that the one may can propose any hypothesis. Okay, so we have to experimentally verify, and if it is matches, then only we can say that this is the correct mechanism. Otherwise, we don't. Even though we cannot say that actually mechanism is like this. This is just our thinking. And I would like to give you some time. Why do you think why do you think it is the mechanism hypothesis one and why not hypothesis two? Anyone want to add? If you don't want to say, you can check. You can message also. What is wrong with hypothesis two and what is right about hypothesis one, and vice versa? Anyone?
Sir, I can answer or I can type the answer, sir.
You can say it. That's good, right? Go ahead.
Okay. Sir, in hypothesis one, sigma complex intermediate can be isolable. We can able to isolate the sigma complex intermediate.
Okay.
Whereas in hypothesis two,
Hmm.
we can't isolate anything.
Okay.
So that isolation of intermediate is a evidence for the mechanism. It support the hypothesis.
Yes.
Isolation of the intermediate.
Okay. Good. Okay. And everyone agrees with that, right? There is no problem. It was quite good, and then involves two step. So that is that answers that there is a two step. Okay, we can say that so there is a two step. There is one step which will give us the intermediate, and then in the second step from the intermediate we can get that. So do you know how to get the intermediate? How will you isolate that? Sometimes it is not trivial to get the intermediate, right? Have you read that we can get the intermediate? Venkatesan, do you know how to get the intermediate?
Sorry, sir. I still have to read once again. Sorry, sir.
No. Your answer is right. Since we are can getting an intermediate, if we can isolate it, we can say that okay, this intermediate was formed. Sometimes we can get the intermediate also, but that's not the same for all the reactions. Sometimes we can get, sometimes we not. Intermediates are isolable. Yes, intermediates are isolable. Now, so I will follow this again. I told also Morrison Boyd. So there is a one how do I say? There is one evidence from kinetic isotope effect that I will share. Okay. So I think you know the kinetic isotope effect, which says that if we replace, let's clear the frame. One, let's say CH bond with the CD bond. So I'll just briefly introduce this. If I replace CH bond with a CD bond, and there will be corresponding rate, right? This will be rate. The corresponding rate will be KH, and the corresponding rate will be KT. So if these two rates are if the rate determining step involves, if the rate determining step involves the breaking of this CH bond. So if we replace CH bond with CD, since this bond is much stronger, so the rate will be slow, and so this KH by KT, this KH KD, the value would be of course greater than 1, and it generally lies between 5 to 8. So this is what is called kinetic isotope effect. Basically, replacement of CH bond by CD lowers the rate, and this ratio we call the kinetic isotope effect. Now what I will show. So for the nitration mechanism, if we do the kinetic isotope effect, there was no effect like this. I mean, meaning that this value was not between 5 to 8. So that the value is very low. So meaning that there is no kinetic isotope effect. I hope this point is clear. So there is no kinetic isotope effect. That is the CH bond breaking. So this CH bond breaking is not the rate determining step. So it's benzene, right? It's benzene. So again I am saying, since there was no kinetic isotope effect, so if there was kinetic isotope effect, the rate will be lower. So but in experimentally there was no kinetic isotope effect. So if even if you replace the hydrogen with deuterium, there is no effect, as such no effect. So there is no kinetic isotope effect, meaning that this bond breaking is not the rate determining step. What is that? Now we can come to the hypothesis 2, which is showed that it's a single step, hydrogen bond breaking and the NO2 bond forming. So if it were like this mechanism, then it should have kinetic isotope effect, because in the one step, and in that step CH bond was breaking. If it were like this, so it should have primary kinetic isotope effect, but it is not. So that's why we can exclude this hypothesis. If it were kinetic isotope effect was observed, then we can say that CH bond breaking was the rate determining step. It would have involved this, and this gives us the mechanism that it's not this step, not this hypothesis. So what will happen? First, we'll let me clear the frame. So let's say our reactant is here. Again, I remember that our E is in that way, potential energy, and there is reaction coordinate. So in the first step, it has a high activation energy to overcome, and it forms an intermediate here, which Venkatesh already told. And in the second step, this has a very low activation energy to overcome, and it can come to the product. So let me do something here. So this is actually little high. Okay. So this is very low. So even if we replace CH or CD, it doesn't matter. So what only matters is this one. So no kinetic isotope effect was observed. Now I have something in the slide which is like this. So please check this. What I have told is already shown here. So it shows progress of the reaction, and then y-axis potential energy. This in the first step it forms this carbocation, and in the second step it goes like this and forms the product. And now you see here in the upper side, what is shown here, there is two activation energy is shown here. In the left side you see there is a high activation energy with respect to this intermediate. It is shown, remember this is shown with respect to the intermediate, and this at the right side you see there is another E activation is written. Now if you replace the hydrogen with deuterium, it will have higher, little bit higher in the right side, little bit higher. Since, but what happened, this at the left side E activation is so high, it doesn't matter. So this all it matters to cross this jump. All it matters is to jump this part and it come to this point, and then whether it is hydrogen or deuterium, it will just move like that and goes on the product. So it's written every this ArHNO2 or ArDNO2 go on to the product. So there was no kinetic isotope effect, and it excludes our second hypothesis. Since we have less time, I will go into the next slide. So let's see the mechanism of sulfonation, which is very similar to the earlier scenario. So this says, and I think you can draw the mechanism. It's very clear, easy. Now the question is the reaction reversible or not? And I pose the second question: how does the reaction differ from the nitration? So the reaction differs from the nitration is that there is some kinetic isotope effect is observed. So remember, I am saying there is some sort of kinetic isotope effect is observed here. So does it mean that it follows the second hypothesis? Actually, it's not. Can we show it in the reaction energy profile diagram? So that I will show clearly here. Now you can see here what is the difference from the nitration mechanism. You see, again, it is the first step which is important, rate determining step. Now in the second step, hydrogen will eliminate and we will get the product here, ArSO3. Now in the upper side, you see what happened. If you replace the hydrogen with deuterium, deuterated substance, there is a equilibrium. Now see the point why there is the equilibrium. Here the activation energy in the left side and right side, if you replace with deuterium, it becomes very much similar to the left side. So the attack of SO3. So that's why there is an equilibrium. So it can move from this part, from right, go to the intermediate and come back to the reactant also. So again, at the upper you can see both activation are very much similar. So it can get revert back to this part. So that's why it's a reversible, little reversible, and you can see the deuterated substance also. This and there is some kinetic isotope effect is observed. So if I read the conclusion here, let me just give me some second. So it is written like this: sulfonation shows a moderate isotope effect. Ordinary hydrogen is displaced from an aromatic ring about twice as fast as deuterium. Does this mean that sulfonation takes place by a different mechanism than nitration? So question, they have posed a question. So does it mean that there is a different mechanism, one involving a single step? Almost certainly not. Again they are saying it's not. So what is the difference is written. Unlike most other electrophilic substitution reaction, sulfonation is reversible. And this fact gives us our clue. Reversibility means that carbocation 2 can lose SO3. So in the middle, in the upper portion, this SO3, this carbocation can lose SO3 to form the hydrocarbon again. Evidently here reaction 2, meaning that going to the product, is not much faster than the reverse of reaction, because these two are very similar. It is not that fast that it will come to the product, because these two yield are the same energy, so it can go back to this. In sulfonation, the energy barriers on either side of the carbocation must be roughly the same height. So these are minute details. Okay, so when someone asks you draw the reaction energy profile for aromatic electrophilic substitution, you automatically can draw this two hump curve, but there is a small difference between how the energies will differ from nitration to sulfonation and other mechanism. So these actually I wanted to highlight points here, and how KI help us to determine the mechanism and provide us our hypothesis. So these two I wanted to discuss. Any question with this second point?
Excuse me, sir.
Yes, go ahead, Venkatesh.
We are comparing, sir, with the hydrogen and deuterium only.
Yes,
with
yes.
the kinetic isotope effect. In the case of sulfonation, sir, if we compare with deuterium and tritium, hydrogen, deuterium, tritium,
yes,
what will be the case, sir?
Then I believe again there will be reversibility. So in that case, it may got back to the product reactant side. For example, if you see this, so assuming this profile is not quantitative. Okay, remember this not quantitative, in qualitative terms. So imagine deuterium, it will be little higher, right? So deuterium, it will be higher. So this energy will be the rate determine it can revert back to the product reactant itself. Then there is a much chance the equilibrium will may lie to the left side. So let me end this with this one small equation which is written. I will try to draw here. It is like very simple, just follow this. ARH, and then plus I have SO3, and there is equilibrium shown here, and K1, and the corresponding will be K inverse, and there is a carbocation ARH SO3, right? And then the second step, K2. This is also related. All these are from kinetics. AR SO3 minus, and then I have H plus. So this is the overall situation. And what they say is that K2 is close to the K inverse. This is the case for sulfonation. In nitration, we will say the K2 rate is very high compared to the K inverse. Okay, so let me check. Yes, K2 is very high, actually it is written very high than the K inverse. So these two reaction differs here. Does it answer? And then tritium, I said it, since what will happen in tritium, so this K2 may be greater than K inverse. So if you put K2, and now for deuterium I am saying very much closer, so it may happen the K2, how can this K2, so K2 maybe is, one second, let me show the mechanism. So here we are calling this K2 will be rate will be slow, mechanism activation energy high, K2 will be slow, sorry. So in that case K2 can be less than K inverse in case of tritium. Okay, rate will be low, rate will be slow. You got it, Venkatesh?
Yes, sir. Yes, sir. Thank you, sir. Yes, sir.
So I am reading this Morrison Boyd book. Any more question? So if the I would like to show some other thing also. Just a second, huh? I have one book here. I don't have time, otherwise I would have shown this one. This is very interesting example from Cartin-Hammett. In the next class, I will try to show this example, okay, from this Cartin-Hammett principle. How do we? It's a little bit complicated system here. From you need to know some stereochemistry to how to get the which product will form with proper stereochemistry. I will try to showcase in the next class, okay, Cartin-Hammett principle. And anything else? Please read books, and I believe that's the best thing you can do. Okay, thank you so much, and I will stop here then and stop recording. And I will share the recording in YouTube so one can go through it later also.